3.5 Derivatives of trig functions. We have the theorems that the limit as x approaches 0 of sine x over x is equal to 1, and the limit as x approaches 0 of cosine x minus 1 over x is equal to 0. Both of these we know with direct substitution would be undefined, but we proved earlier in the book by squeeze theorem that these limits were true. And now in this chapter, in the section derivatives of trig functions, we're going to use these limits that we know and manipulate them in some other way. So for the homework section number 7, I have that the limit as x is approaching 0 of sine 3x over x. How do we find the limit? It's not an identical. I cannot say it equals 1. So I'm going to manipulate it by multiplying it by 1, or a 3 over 3. The book describes it as multiply by 3, divide by 3. So our next line here, we have that we just went ahead and did the multiplication from here and here. And then I'm going to use the property that I'm just going to factor out a 3 out of the numerator. It's basically saying this is like multiplication. So I can pull it out as a c times the limit. It was one of the laws that we had. And then I have now the limit as x approaches 0 of sine 3x over 3x. And if this is the case, this is starting to look more similar to what we have in our theorem. So we're going to do some substitution. We're going to let t equal 3x, and we're going to substitute t in. So now I have here in this line that 3 times the limit as t goes to 0, that's a t, of sine t over t. And this now matches what our theorem has, and we know that this goes to a limit of 1. So I now have 3 times 1, or a limit of 3. If I want to do example 9 from the homework, I have the limit as x approaches 0 of sine 7x over sine 3x. So I'm going to multiply by 1. I'm going to change the look of these equations by saying it's sine, I'm going to multiply 1 over x by 1 over x, and I distribute this in, and I get this expression here. I'm going to multiply the numerator and the denominator by 7 over 7 and 3 over 7. Or you can think of it as we can multiply each the numerator and denominator by 1. So then I have, once it's distributed, I have what seems similar to what we had in the previous example, and I'm going to be doing it twice. So I'm going to be pulling out its numerators of each, the numerator and numerators, and then saying the same process. We're going to do the substitution. We're going to have that it reaches the same exact look of the theorem, and we can substitute in the limit of 1, and then we have 7 thirds times 1, and our answer would be 7 thirds. If we want to prove what the derivative of sine x is, we're going to use our original definition of derivatives, where f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That's this line. So we're going to use it with sine x. And we plug it in. We have sine x of x plus h minus sine x over h. I then use the angle sum formula from trigonometry. So that sine of x plus h now becomes sine x cosine h plus cosine x sine h. And then left is that minus sine x. From there, I went ahead and I rearranged it. The last two terms, I switched positions, so I have the negative sine x plus the cosine x sine h. And then from the first two terms, I factored out a sine x. So from here, I went to here. Sine x times cosine h minus 1. I left this third term alone. But then I noticed that I technically have, instead of 3 terms in the numerator, I went down to two terms in the numerator, and I can use our sum of limits rule. And I broke this into two limits. And then from there, when I go to the red line, I went ahead and said, okay, this is h going to 0. The sine x is technically going to be a value that I can factor out like a multiplication. So I pulled that sine x out times the limit as h approaches 0 of cosine h minus 1 over h. And now this looks like our theorem that we had earlier. Second term, I did the same thing, pulling the cosine x out, and it's multiplying the limit of sine h over h as h approaches 0. And it matches our previous theorem. So then I'm going to go ahead and I have sine x. I'm going to substitute in my limits. So sine x times 0 plus cosine x times 1. And then sine x times 0 is 0. So my final is the derivative of the function f of prime is cosine x. This proves that given the function f of x equals sine x, its derivative is cosine x. And that's what we have for theorem 3.12. Derivatives of sine and cosine x. Cosine x can be proved the same process. That the derivative of cosine x equals negative sine x. So two examples from homework. Number 17, y equals sine x plus cosine x. And we just take the derivative of each using our limit laws. So we have cosine x minus sine x. 19, I have a product going on. I need to use the product rule. And I'm going to go ahead, but it's involving e and a trig function. So I went ahead using the product rule, derivative of the first times the second function. And I have the first function times the derivative of the second function. I did then factor out an e to the negative x, and I have my final answer. From here, theorem 3.13 is the list of all 6 trig functions' derivatives. And I walked through problem 30 from the homework section because in the homework section, I proved sine of x and its derivative, but you can walk through any of these trig functions and prove its derivative, and that is what number 30 is. We're going to prove the derivative of secant x, and I'm going to use the product and quotient rules, but in this case, it's just one term. But what I did was I put it in cosine sine form. Because as of right now, the only one we've proved are those two, essentially, sine x and cosine x. So I have it secant x equaling 1 over cosine x, and then I'm going to use the quotient rule, and I have my d high, low, d low, using the low d high minus high d low over low squared quotient formula. I went ahead, did my quotient rule, and notice once you get down to this, that does not look like what we had for the derivatives. So they separated these factors out. So the numerator is really 1 times sine x, and the denominator, instead of cosine squared, we have cosine x times cosine x. And then I can say, okay, this is really secant x, and this is really tangent x, putting it back into a simplified form. So we just proved where that trig derivative came from. I did a homework problem number 38. We have the function y equals tangent x over the quantity 1 plus secant x. So if this is the case, I'm going to use the quotient rule again. I set up my d high, low, d low over to the side in blue, and I use the quotient rule. So my formula here is low d high minus high d low over low squared. So then it now becomes completely just manipulation and simplifying this expression. So what I did was, for the next line here, I distributed the secant squared into that first binomial, the 1 plus secant x, and then I distributed the tangent, into the second term. And then I see that I have secant tangent squared of x. And because everything else inside this expression is secant, I'm just left with this oddball tangent squared. So if I can try to get rid of that by substituting something in for it, I can simplify this easier. So I substituted a trig identity. Remember, our trig identities would have been 1 plus tangent squared of x is equal to secant squared of x. So I substituted for tangent squared of x, secant squared of x minus 1. That's what I substituted in. Now, everything in this expression is in terms of secant. And then I distributed that last term of here. I distributed that secant x in. And then I see that I have some that reduced. And I was left with secant squared of x plus secant x over, remember, low squared. But then I see I can have a GCF, so I factored out a secant x, and I was left with a quantity secant x plus 1. I have 2 in the denominator. Yes, they're written differently, but they're both positive. This numerator's expression can be rewritten as 1 plus secant x, and then I can see there was 2 in the denominator, so it reduced, and leaving 1 in the denominator only. So my final answer for this one's derivative is secant x over the quantity of 1 plus secant x. Last thing we have to talk about is higher order of trig derivatives. And we can see that no matter how many times you want to take the derivative, we just keep applying the process that we've been doing. So for the homework example, I have number 42, y equals cosine x. The book asks find second derivative, or y double prime. So you go through the process and you say first derivative is negative sine x. Second derivative is you're leaving the negative and you're taking the derivative of the sine x, which is negative cosine x then. But if I wanted to find the fourth derivative of this, I just keep going. So the third derivative of that is then positive sine x. And taking the derivative of that again is cosine x. Notice, it took us to get to the fourth derivative to get back to our original function. Yes, this is the fourth derivative, but it came back to the original function. That means we cycled back. It cycles back, and all trig functions end up being cyclical. And we can then repeat, and eventually we will get back to where we were originally.